Suppose we have a function of two variables defined on a region in the xy plane, and this region contains a point xp, yp. Then the function at the point P has a local maximum value if the value of the function at this point is larger than or equal to all the values of the function of x and y for all domain points x and y in an open disk that's centered at point P. So for example, if we look at this paraboloid, we have a local maximum value at this point. Because if we take a disk around this point, so this disk is parallel to the xy plane, then the value of the function at this point is larger than all the values of the function in that disk. And similarly, we define a local minimum where the value of the function at the given point is smaller than or equal to all the values of the function, so for all the domain points x and y in the open disk centered around the point. So if this paraboloid was flipped over, then this point would instead be a local minimum. And note that the tangent plane at a local minimum or maximum is horizontal. So here, the tangent plane is parallel to the xy plane. And similar to functions of one variable, local extrema are also called relative extrema. Now to find a local minimum or maximum, we use the first derivative test. So if the function has a local minimum or maximum value at an interior point of its domain, and if the partial derivatives exist at this interior point, then the partial derivative with respect to x evaluated at the point is equal to 0, and the partial with respect to y evaluated at point P is also 0. And we can show this using the directional derivative. So if the derivative of the function in an arbitrary direction is equal to the dot product between a gradient vector and the direction vector, so recall that was equal to the partial of f with respect to x by the x component of u plus the partial of f with respect to y by the y component of the direction vector. So no matter which direction we're evaluating the derivative, the slope of the tangent to the curve along that direction is 0. So this applies to all the directions. So therefore, for this to be true, the partial derivatives must both be 0 for an arbitrary direction, such that the directional derivative is 0. And recalling the equation for the tangent plane was the partial with respect to x evaluated at P by x minus xp plus the partial of f with respect to y evaluated at P by y minus yp minus z minus zp is equal to 0. So given that the partial derivatives are 0 at a local maximum or minimum, then we obtain z is equal to zp. So this is a horizontal plane with the normal pointing in the z direction. Now furthermore, a critical point of the function is an interior point of the domain of the function where both the partial derivatives with respect to the x and y direction are 0, or where one or both of these partial derivatives does not exist. So a function can only take on extreme values at critical points and boundary points. And furthermore, a differentiable function of two variables has a saddle point at a critical point in the domain of the function, so it has coordinates xp and yp, if in every open disk that's centered at this point, there are points in the domain of the function where the value of the function at the point x and y is larger than the value of the function at point P, and also the value of the function at x and y is smaller than the value of the function at point P. So the corresponding point on the surface, which has coordinates xp, yp, and the z coordinate, is the function of the surface evaluated at xp and yp, is a saddle point of the surface. So this can be seen if we draw a disk around this point, where the disk is parallel to the xy plane, so its face is normal to the z-axis. So we see that a point on this parabola that's in the plane parallel to the yz plane has a higher value than the function evaluated at point P. And similarly, a point on a parabola that's in the plane parallel to the xz plane has a value that's smaller than that of the function evaluated at point P. So this is neither a local minimum or maximum, but a saddle point. So we can see this surface looks like a saddle. We saw the partial derivatives of a function of two variables with respect to x and with respect to y were both equal to 0 at a critical point, and this did not guarantee that the function had a local minimum or a local maximum at that point. And we found this condition using the directional derivative in an arbitrary direction u. So that was a dot product between a gradient vector and the arbitrary direction vector, which was the partial of the function with respect to x by the x component of the direction vector plus the partial with respect to y by the y component of the direction vector. So both of these partial derivatives must be 0 to guarantee the derivative of the function to be 0 in all directions at the critical point, being an interior point in the domain of the function. Now, similar to functions of one variable, we can take the second derivative. So we'll take the second directional derivative, which will denote d2 in shorthand form. So this is the second derivative of f in the direction of u. So that's equal to the dot product between a gradient of the directional derivative. So in this case, it'll be the partial of f with respect to x by u1 plus the partial with respect to y by u2. And we take the dot product with u hat. So recall the gradient operator on some function was the partial with respect to x in the I direction plus the partial with respect to y in a j direction. So we get the second partial derivative of f with respect to x by u1 plus the partial derivative of the partial with respect to y with respect to x. So that's the component in the x direction plus the component in the y direction, which is a partial of f with respect to y. So we get the second partial derivative with respect to x and y by u1 plus the second partial derivative of f with respect to y by u2 in the j direction. And we take the dot product with the direction vector u. So that was u1 in the x direction plus u2 in the y direction. So let's simplify this over here. So we get the second derivative of the function f in some arbitrary direction in the xy plane, and we multiply the I components together. So we get the second partial of f with respect to x by u1 squared plus the second partial derivative of f with respect to y and x by u2 by u1 and plus the second partial derivative with respect to x and y by u1. So this second component is multiplied by the second component of the direction vector. So we have u2 and plus the second partial derivative with respect to y by u2 squared. So by Clairaut's theorem, if the second partial derivatives are continuous, then these two partial derivatives are equal. So we can add 2 here and get rid of this term. And we recognize this is a quadratic form, which we can write as follows. So let's get rid of this. So this can be written in the form of the transpose of a vector u by a matrix, which is called the Hessian matrix for this particular problem, and multiply by the vector u. So in matrix form, we have the transpose of the vector u being the direction vector, and we have a square symmetric matrix with the second partials with respect to x and y on a diagonal, and we have 2 of the partial with respect to x and y, so we put one of each of these in the remaining entries, and that's multiplied by u, which has components u1 and u2, and that's equal to our second derivative of our function in the direction of u. Now keeping this aside, we'll write the second derivative test. So let's get rid of this. So the second derivative test to determine what type of local extrema we have involves a continuous function of 2 variables with continuous first partial derivatives, and the second partial derivatives are also continuous throughout a disk that's centered at a critical point. So the partial derivatives evaluated at this point are both 0. So we have the partial with respect to x being 0, and also the partial with respect to y at the critical point being 0. So given these criteria, we can identify 3 conditions, and the first one is where the function has a local maximum at the critical point with coordinates xp and yp. So for the function to have a local maximum, the second derivatives evaluated at this point in all directions must be negative. So that's similar to the case where we had a function of one variable, where the curve was concave down. Except for functions of 2 variables, we have infinitely many directions. So these conditions can be obtained from the Hessian. So what we do is take the Hessian as the determinant of the Hessian matrix containing the second order partial derivatives. And let's do that over here. So the Hessian, being the determinant of this matrix, is obtained by multiplying the cross terms and subtracting them from each other. So we have the second partial with respect to x, while the second partial derivative with respect to y, minus the partial with respect to x and y squared. So let's move this up here. So if the Hessian, being the determinant of this matrix, is larger than 0, then that guarantees this quadratic form of the second derivative in the direction of u is either positive definite, so it's always positive for every direction vector, so in all directions, or it's negative definite, so the second derivative is less than 0 no matter what the direction vector is. So that's what a positive Hessian tells us. So the positive definite property means that the Hessian matrix has all positive eigenvalues, and a negative definite property means the Hessian matrix has all negative eigenvalues. So because we want a local maximum, then the partial derivatives on a diagonal are both negative. So therefore, if the second partial derivative with respect to x is less than 0, then that means we have a negative multiplied by a negative gives a positive value, and therefore if the Hessian is larger than 0, then the function has a local maximum at this point. And similarly, our function has a local minimum at the critical point P if the second derivative of our function in the direction of u is larger than 0. So this condition also means that the Hessian is larger than 0, but the partial derivatives on a diagonal are both positive. So if the partial with respect to x is positive and the Hessian is larger than 0, then the function has a local minimum at this point, as the directional derivative will always be larger than 0. So you can remember these conditions by making analogies with functions of one variable. And this brings us to the third condition, where f has a saddle point at the critical point if the second directional derivative is positive in some directions and negative in some directions, or this quadratic form is indefinite. So this condition is where the Hessian is less than 0, meaning the eigenvalues of the Hessian matrix are both positive and negative. And in our fourth condition, the test is inconclusive, where the Hessian evaluates to 0. So these are the conditions that come out from the positive definiteness of the quadratic form of the second directional derivative. So let's have a look at a couple of sample graphs here. So for our hyperbolic paraboloid, we see that at the critical point, we have a second derivative in the x direction being less than 0. So the curve is concave down. So this means that the second partial derivative with respect to x is less than 0. But in the y direction, so we have the second derivative in the j direction, we see that the curve is concave up. So the directional derivative is larger than 0. So we see that fyy is positive. So basically we evaluate these partial derivatives and evaluate the mixed derivative and you'll find that the Hessian is less than 0. So that's the third condition, where the function has a saddle point at the critical point. And if we look at this inverted paraboloid, then we see the second directional derivative in the x direction is less than 0, so the curve's concave down, and in the y direction it's also smaller than 0. So these directional derivatives are the same as the second partial derivatives in the x direction and the y direction. So negative by negative is positive, and we have no xy terms in the equation for a paraboloid. So the Hessian in this case is larger than 0. So we've satisfied these two conditions, and therefore the function has a local maximum at this point. And note that this term over here will always be positive given it's a squared term, and this will apply to surfaces with mixed terms, like a surface, for example, with terms like x multiplied by y. And applying these conditions takes practice, and they're best illustrated in example problems. We can find the absolute or global extrema, being the global minimum and global maximum of a continuous function of two variables on a closed bounded region. And we'll list the steps while covering an example. So here we have a hyperbolic paraboloid defined by the following function, being y squared minus 4x squared, and we're looking for the global extrema on the closed region that's bounded by this rectangle. So all the points in this rectangle have an x coordinate that's between minus a half and a half, and a y coordinate between negative a half and a half. So the first step is to find the local extrema, being the local minimum and maximum at the interior points of the region. So again, our closed region is this rectangle. So in 3 space, our boundary looks something like this. So we're cutting the surface by a plane at x equals 1/2, and a plane at x equals minus a half, being at the back of this surface, and another plane cuts the surface at y equals 1/2, and y is equal to minus a half. So that's our bounded part of the surface, which is bounded on all sides. So to find the local extrema at the interior points, we find the critical points by taking the partial with respect to x, which gives minus 8x, and the partial with respect to y gives 2y. And setting these partial derivatives to 0 gives our critical point at x equals 0 and y equals 0. So therefore the z coordinate of our critical point is 0, which is the only critical point. And the next step is to find the local extrema, being the local minima and maxima at the boundary points of the region. So to do that, we'll look at each boundary line separately. And now let's look at this boundary line first, at x equals 1/2, which cuts the surface into the following curve, being a parabola. And we first check the interior points. So this curve is defined by the function of x is equal to 1/2, and y is the variable. So what we get is y squared minus 4 by 1/2 squared, which is 1. So if we differentiate this function, we get 2y, and setting this equal to 0, we get one interior point where the derivative is 0. So that's at y is equal to 0, which is this point over here. So at y is equal to 0, we have the function at 1/2 and 0 evaluating to -1. And now we check the endpoints of the boundary. So at point A, where y is equal to 1/2, so we have f of 1/2 and 1/2. We have 1/2 squared, which is 1/4, minus 1 is -3/4. And similarly, at y is equal to -1/2, we also get the function evaluating to -3/4. So now we've covered this boundary line, including the endpoints. And now if we cover the boundary line from A to C, so that would cut a curve in this surface from A to C. We have the function where x is variable and the y coordinate is fixed at 1/2. So this evaluates to 1/4 minus 4x squared. And now checking the interior points of this boundary by setting the derivative to 0. So the derivative evaluates to -8x, which if we set to 0, we get a maximum point on this curve at x is equal to 0. So we have the function at 0 and 1/2 evaluating to 1/4. So that's this point over here. And because we already checked the endpoint in the previous boundary, we already covered A. And by symmetry, the endpoint at C evaluates to the same z value. And you can verify this by substituting x is equal to -1/2 into this equation. And you'll get the same z value as we did previously. So we now covered this boundary. And by symmetry, we're going to get the same result if we check the boundary line from C to D and B to D. So the final step is to identify the absolute or global extrema, or the global maximum and global minimum. So to do that, we're going to list the candidates that we found from the previous steps. So these candidates are where z is equal to 0, -1, -3/4, and 1/4. So the global maximum is 1/4, and this occurs at x equals 0 and y is equal to 1/2. So that would be over here. And the global minimum is -1, which occurs when x is equal to 1/2 and y is equal to 0. So that's this point over here. And note that the global maximum also occurs at y is equal to -1/2, and the global minimum also occurs at x is equal to -1/2, which we can see by the symmetry of the surface. Let's find the local extrema and or saddle points for the given function. So given the function's unbounded, we find the critical points by taking the partial with respect to x. So that gives 3y minus 3x squared. And the partial with respect to y gives 3x minus 3y squared. And we set these partial derivatives to 0. So from the first equation, we have y is equal to x squared, which we substitute into the second equation. So we get 3x minus 3 by x to the 4. And that's equal to 0. So dividing through by 3 and factoring out x, we get 1 minus x cubed. And that's equal to 0. So we have a critical point at x equals 0 and x equals 1. So our critical point at x equals 0 has a y coordinate of 0, and a critical point at x equals 1 has a y coordinate of 1. So evaluating the function at the critical point, we get 0, and at the other critical point, we get 3 minus 1 minus 1. Now to determine the type of critical point, we evaluate the second derivative with respect to x. So that gives minus 6x. And with respect to y, gives minus 6y. And the mixed derivative with respect to x and y. So we just differentiate the partial with respect to x with respect to y. So we get 3. So our Hessian is the product of the second order partial with respect to x and y. So we get 36xy and minus the mixed derivative squared. So at our first critical point, the Hessian is negative 9. So that's less than 0. And therefore we have a saddle point. And at our other critical point, the Hessian is 36 minus 9, which is 27. So that's greater than 0. So that could be a local minimum or a maximum. So we check our partial with respect to x, which is minus 6 by 1 or minus 6. So that's less than 0. So the curve is concave down, and we have a local maximum at this critical point. Find the global maximum and minimum for the paraboloid on a closed triangular region bounded by the x-axis, the y-axis, and a line y equals 1 minus x. So at x equals 0, y is equal to 1, and when x equals 1, y equals 0. So first we check the interior points. So taking the partial with respect to x, we get 2x, and the partial with respect to y gives 2y. And setting these equal to 0, we get a critical point at x equals 0 and y equals 0. Now given that this point lies on a boundary, it's actually a boundary point and not a critical point. And now we'll check the boundary points. Starting with the horizontal line, AB. And now we check the interior points of the boundary line. So we have the function where x is a variable and y is constant at 0. So that's equal to x squared. And taking the derivative, we get 2x. And setting the derivative to 0 gives x is equal to 0. So again, we get the function evaluated at 0, and 0 gives 0. So we'll take this as one of the candidates. And now we'll check the other endpoint of the boundary, which is at x equals 1. So that evaluates to 1. And this is another candidate. And now we'll check the line from A to C. So we get the function at x equals 0, with y being a variable, is equal to y squared. And again, taking the derivative, we get 2y. And setting it equal to 0, we get y is equal to 0. So again, we get the function evaluated at 0 and 0 is equal to 0. So we already had this candidate, and we'll ignore it. And then evaluating the function at the endpoint of the boundary, we have f of 0 and 1, which gives 1. So these two candidates evaluate at the same value, so we'll ignore this one. So now we've checked boundary line AB and AC, including the endpoints. So finally we check the boundary line BC. So what we have is a function of x and y, where y is 1 minus x, is equal to x squared plus 1 minus x squared. And simplifying this, we get 2x squared minus 2x plus 1. And differentiating, we get the derivative at x and 1 minus x, evaluating to 4x minus 2, and setting this equal to 0, we get x is equal to a half. And therefore the function at x, which is a half, and 1 minus x is also a half, is 2 by 1/2 squared, or 2 quarters, minus 2 by a half, plus 1. So we get another candidate at f of 1/2 and 1/2, which is equal to a half. So therefore our candidates are 0, 1, and a half. So our global maximum is 1, and our global minimum is 0, which occurs at x equals 0 and y equals 0. Find the global maximum and minimum of the following function on the given parameterized curve. So here we have a quarter circle of radius 1. So when t is equal to 0, x is equal to 1 and y is equal to 0. And when t is equal to pi on 2, x is equal to 0 and y is equal to 1. So here we can write this as a function of one variable. So we have f of x of t and y of t is equal to cosine t minus sine t. And to find the critical point, we can take the derivative of f with respect to t and set it equal to 0. Or we can apply the chain rule. So the partial of f with respect to x is 1 by dx dt, which is minus sine t, plus the partial of f with respect to y, which gives minus 1 by dy dt. So that gives minus cosine t. And setting this equal to 0, we get minus sine t is equal to cosine t, or the tan of t is equal to minus 1. So that evaluates that t is equal to minus pi on 4, which is outside the boundary. So evaluating the function at the endpoints, we get the function at x equals 1 and y equals 0, or t equals 0 is equal to 1. And at the other endpoint, we have the function at x equals 0 and y is equal to 1, evaluating to minus 1. So the global maximum is 1, and the global minimum is minus 1 on the given parameterized curve. Determine whether the function has a maximum, minimum, or saddle point at the origin. So if we take the partial derivative with respect to x, we get y squared, and the partial with respect to y gives 2xy. So setting this to 0, we find that the origin is a critical point. And taking the second partial derivative with respect to x, we get 0, and with respect to y gives 2x. And the mixed partial derivative with respect to x and y is equal to 2y. So at the origin, all of these derivatives evaluate to 0, and therefore the Hessian is equal to 0. So the second derivative test does not provide us any information on the nature of the critical point. So doing a bit of further analysis, we see that the function along the x-axis, so x is a variable and y is 0, gives 0, and in the orthogonal direction along the y-axis, the function at x equals 0 and y is a variable is also equal to 0. So that also does not give us any information. So what we'll try is evaluating the function along the line y is equal to x. So we take the function of x, and that gives us x cubed. So therefore for negative values of x, the function evaluates to a negative value, and for positive values of x, the function is always positive. So if we took a small disk around the origin at the critical point, we see that the point is neither a minimum or a maximum, and we assume it's a saddle point.